So this is our last week of the semester. And so we're going to finish the semester off by ending with Chapter 7. Chapter 7 focuses on energy from alternative sources. And so we've already learned about energy sources such as coal, petroleum, which is a crude oil product. Included in that also, we looked at natural gas, which is mostly methane. And then we also focused on some other crude oil products, such as octane. And so in this chapter, we're going to be looking at some other alternative sources. In chapter 6, we introduced a few of those, such as biofuels that are from cellulose, as well as non-cellulose sources. Non-cellulose sources being things like corn, which is used to produce ethanol, and then some other alternative sources like biofuels. In addition, biodiesels. We looked at biodiesels, which are made from different vegetable oils. In this country, one of the main sources is used cooking oils in restaurants that are recycled, and that used cooking oil is then used to make biodiesel. And so some other alternative sources that we're going to focus on in Chapter 7 are going to be nuclear energy, as well as solar, wind, and geothermal, as well as hydroelectric or water alternative sources. So in Chapter 6, we introduced the terms renewable energy resources versus non-renewable energy resources. And so in Chapter 6, we focus mostly on those non-renewable energy sources like coal, oil, petroleum, natural gas. All of those are non-renewable sources that originate and we come from decaying plant matter, and therefore we call those fossil fuel-based non-renewable energy sources. However, we looked at some renewable sources like biodiesel and biofuels, which are plant-based sources. In Chapter 7, looking at nuclear energy as an alternative to fossil fuels. However, nuclear energy is also non-renewable because nuclear energy derives from uranium, and there is a limited amount of uranium on the planet. And that uranium has to be mined in a similar way that coal has to be mined. And so therefore you have those disadvantages of nuclear, but it is an alternative to fossil fuels because in using nuclear energy, you don't produce greenhouse gases like CO2. Those are not produced by burning nuclear based fuels. Also, you don't have sulfur-based compounds that are emitted from a nuclear power plant like you have from a coal-burning power plant, and therefore you don't have precursors to acid rain that are produced. So those are some advantages of nuclear over fossil fuel-based energy sources like coal. You don't get the bad emissions like CO2 and other greenhouse gases and sulfur-based compounds, which are air pollutants, as well as precursors to acid rain. And also you don't produce the nitrogen oxides, which are also air pollutants, and also precursors to acid rain. So there are some advantages of nuclear over fossil fuel-based energy sources, but nuclear is also a non-renewable energy source. And so after looking at nuclear and comparing nuclear power plants to fossil fuel-based power plants, we're also going to take a look at solar energy and then some other types of renewable energy sources like wind, geothermal, and hydroelectric. And looking at how these different renewable energy sources are assessed in terms of their environmental impacts as well. And so in this graph of the world energy consumption, of quadrillion British thermal units, BTUs, which is a British unit of energy, which you can convert into metric or SI system unit of energy like kilojoules or joules. And then on the x-axis, you have the years. And this graph shows you on a worldwide basis the amount of energy that's being consumed by the various energy sources. And so the red trace here is nuclear. So we can see that between 1990 and the present, and this data is good up to the year of 2015. Everything beyond 2015 is a projection. And so we see that nuclear energy usage worldwide has remained pretty stable from 1990 through 2015, not a big difference. And then there's been a slight increase and a slight projected increase, but very, very small increase in nuclear power usage between 2015 through 2040. So it's projected that there will be a slight increase in the amount of energy consumed by nuclear sources, but not a big increase. What we see some big projected increases in is the renewables, the green graph. So it's projected that between 2015 and 2040, that the increase will be almost twofold of renewable energy uses. Then when you look at some of the other sources that are non-renewable, natural gas and petroleum, the blue and the orange graphs, you also see a projected increase, but not as steep of a slope of a line, and therefore not as great of an increase as renewables, but still an increase in the use of petroleum and other liquids, as well as the blue graph, natural gas. And this is projected, as you can see, the natural gas, the blue graph, you can see that from 1990 through the present, there's a steady increase in the amount of natural gas used worldwide, and then it's projected to further increase. And this is this projected increase is due to the predicted increase in the amount of fracking that we learned about in Chapter 6 that is going to continue to increase worldwide. And so, in looking at that global energy consumption graph, which projects our usage of energy and what sources we're going to be using for our energy through 2040, we see that the greatest increase is renewables. And so there may be many reasons why we feel that there's going to be this great increase in renewable energy resource use as well as natural gas use through 2040. And our red graph, the nuclear energy graph, there's going to be just an ever so slight increase, but pretty flat. And why is that? Why is nuclear not projected to be the most popular thing going in the next 20 years as far as energy consumption source? And so let's start off by talking about the bare basics of nuclear energy, how nuclear energy is produced, and then we're going to take a look at nuclear power plants. And so nuclear energy is obtained via a nuclear reaction that is called nuclear fission. Nuclear fission is the splitting of a large nucleus into smaller nuclei, and this splitting process also results in a release of energy. And so you get a release of energy because the total mass of the products is going to be slightly less than the total mass of the reactants. And due to the law of conservation of energy, that matter, that mass can't be just really lost. It has to be converted into something else. And what that something else is energy. So this quote unquote missing mass, which is not missing mass, that mass has just been converted into energy, it's going to be about 0.1% of the original mass of the reactants. And so that energy is going to be equal to according to Einstein's famous equation, the mass times c squared, c being the speed of light. And we learned that quantity back in our chapter when we learned about electromagnetic radiation. The speed of light is equivalent to 2.99 times 10 to the 8th meters per second. And you've also known it to be simplified to being just 3 times 10 to the 8th meters per second. So if you are going to perform a nuclear fission reaction, energy to get that energy released, and you start off with 1 kilogram of a radioactive element, uranium, uranium-235. And so uranium symbol is capital U, and that dash in 235, the 235 is the mass number. And the mass number, as we recall from our previous chapter, is the number of protons plus the number of neutrons. And so therefore, in using Einstein's famous equation, the energy that's released, capital E, that energy is released as a result of the splitting of the nucleus of uranium-235. Inside that nucleus of uranium-235, of course, we have protons and we have neutrons. So there is a total of 235 as far as our mass number. The number of protons plus the number of neutrons is equal to 235. And so the E, the energy released, is going to be equal to the change in mass, which is our delta symbol, so delta M, times the speed of light squared. And so if you have one kilogram of uranium-235, and if the mass of the products is 0.1% less than the original mass of the uranium-235, then what is the change in mass? Well, the change in mass is going to be 1 kilogram times the fraction that represents 0.1%. And so you take your 0.1% and change to a decimal. And therefore, in changing that to a decimal, 0.1, we move that decimal 2 spaces to the left. And so you got 0.001. So you got 1 times 10 to the negative 3 kilograms. That's going to be your change in mass, your delta M. So the energy is going to be equal to the delta M, the change in mass, times the speed of light, but the speed of light has to be squared, raised to the second power. And when you raise the speed of light to the second power, or square it, not only do you have to square the numerical portion of the value of the speed of light, but you also have to square the units. So that becomes meters squared per second squared. And so now you do your math. 2.99 times 10 to the 8th. You put that in your calculator, and then you access your square function. And for most calculators, that is going to be an x, and then you'll see raised to the second power. So it's going to be this key here. So 2.99, and then I need to access my exponential function, the EXP key for this calculator, or it may be the double letter E on your calculator. And then I want to square it, so I hit the square button. And then I need to multiply that times 1 times 10 to the negative 3. And so make sure you're accessing the correct functions on your calculator. And so in doing our math, we get 8.94 times 10 to the 13th kilograms meter squared per second squared. So you may say that, well, that's not an energy unit, is it? Kilogram meter squared per second squared. Well, one cool thing is that 1 joule is equal to 1 kilogram meter squared per second squared. And so you can convert the kilogram meter squared per second squared into joules by using that conversion factor. So there's our energy in joules, because 1 joule is the same thing as 1 kilogram meter squared per second squared. And so using 1 kilogram of uranium-235 under a nuclear fission reaction produces the same amount of energy that's equivalent to 22,000 tons of the explosive TNT. So you can obtain a tremendous amount of energy from a very small amount of matter. That's a very small mass of matter, 1 times 10 to the negative 3 kilograms, which is about 1 gram. So 1 gram of uranium-235 that undergoes nuclear fission gives you the same energy output as an explosion of 22,000 tons of TNT. TNT is also called trinitrotoluene. There's its molecular structure there. It was discovered by Alfred Nobel in 1863. It became the standard of explosive power as a result of the birth of nuclear weapons. And so that's how they were able to judge the strength of a nuclear reaction when they were doing the research into making the first nuclear weapon is comparing its explosive strength of the nuclear weapon to that of TNT. TNT is a very unstable molecule, so it explodes very easily. So 2 moles of TNT, they'll rearrange to form 15 moles of hot gas. So when it explodes, it gets converted into nitrogen gas, carbon monoxide gas, and water vapor, plus some carbon. So about 1 gram of TNT is going to produce about 1 liter of this mixture of hot gases. So therefore, when it explodes, its volume increases by 1,000 times. That's just how powerful a TNT explosion is. And so elements that undergo nuclear fission are a very special class of elements that are on the periodic table. Not all elements are capable of undergoing nuclear fission. In other words, not all elements are radioactive. But for those that are radioactive, you can split their nucleus into smaller nuclei. And so before we go into nuclear reactions, let's go and review the concept of isotopes. We remember that from our previous chapter, I think chapter either 1 or 2, that isotopes are basically the same element. So they have the same number of protons and electrons if we're talking about neutral elements. But what's different about different isotopes of the same element is that they have different numbers of neutrons. So we recall discussing carbon-12 versus carbon-13 versus carbon-14. The difference between those is that carbon-12 has 6 protons and therefore 6 neutrons in its nucleus, whereas carbon-13 has 6 protons but 7 neutrons in its nucleus, whereas carbon-14 also has 6 protons in its nucleus but 8 neutrons. And so that's the difference between those 3 different forms of carbon, those 3 different isotopes of carbon. They have different numbers of neutrons. And so when we write the symbol for an isotope of an element, you use both the mass number and the atomic number. And the atomic number, of course, is the number of protons. And so uranium-238 means that the uranium has a mass number of 238. And so the mass number is written as a superscript. And then the atomic number, which you find directly on the periodic table for uranium, is the number of protons. And therefore, the atomic number is written as a subscript. And of course, we remember if it's a neutral atom, then you have the same number of protons and electrons. And so uranium-238's isotopic symbol is written this way. The symbol of the element, uranium, is capital U. Then the superscript that's written in front of the symbol for the element is the mass number. The subscript that's written in front of the symbol of the element is the atomic number. And then we also recall that the atomic mass is the weighted average of all of the mass numbers that exist for all of the isotopes of that particular element. And it's based, that atomic mass, of course, is always going to be based on the fractional abundance of each isotope. And so that's how the atomic mass is calculated. For each element, it's based on the mass numbers and the fractional abundance of each isotope that exists for that element. And so nuclear fission reactions, which split a large radioactive element's nucleus into smaller nuclei, it has to be initiated by a neutron. And so the symbol for a neutron with a 1 superscript and a 0 subscript, and then the lowercase n symbol for neutron. So a neutron has a mass of 1, and a neutron is neutral. So it has no charge. No protons. So its atomic number is 0, and its mass number is 1. And so a neutron will hit the nucleus of a radioactive element like uranium-235, for example, with the mass number of 235. Atomic number of uranium is 92. So when it hits, that neutron hits the nucleus of uranium-235, you produce another isotope of uranium that's very, and that's uranium-236. That's why you have the brackets around this isotope, because this isotope is so reactive that it doesn't hang around very long. So because it's so reactive, it's going to immediately start to split. And that's where fission takes place. So the fission or the splitting of uranium-236, it splits into barium-141, krypton-92, and then the other product is 3 neutrons. And so now those 3 neutrons that are product of the fission of uranium-235, those neutrons can go on and therefore bombard and hit the nuclei of other uranium-235 atoms. And therefore, the nuclear fission reactions will keep going on and on and on and on, because every nuclear fission reaction produces more neutrons, and those neutrons can go on and bombard other radioactive nuclei and produce more fission reactions. And so we note that this fission reaction for uranium-235 is balanced. It is a balanced nuclear reaction. So what do I mean by a balanced nuclear reaction? Well, that means that the superscripts and subscripts on both sides of the arrow, they add up to be the same total. So notice here for the first part of the reaction, the superscripts, you've got a 1 and a 235. So that's total 236. The subscripts, you have 0 and 92, giving you a total of 92. On the right-hand side, you've got 236 and 92. So that's totally balanced. And then on the far right-hand side, the subscript, you've got 56 plus 36 plus 0, which gives you 92. And then the superscripts, you've got 141 plus 92 plus 3 times 1. You've got to account for the fact you've got 3 neutrons. So 3 times 1, which is 3. So 3 plus 92 plus 141 gives you 236. So that's what it means by having a balanced nuclear reaction. The sum of the superscripts and the sum of the subscripts on the left and right-hand sides of the arrow must be the same. And so I talked about the fact that one of the products of the nuclear fission of uranium-235 were these 3 neutrons. So those 3 neutrons, they have the ability to go on and bombard the nuclei of other uranium-235 atoms, and therefore cause them to split, producing even more neutrons, which can go on and split more uranium-235 nuclei. So this is called a chain reaction. It keeps going and going and going until there's no more uranium-235 available. And that is what is considered spent nuclear fuel. And that means that the nuclear reactor now has got to get rid of all this spent nuclear fuel. There's no more uranium-235 available to be split. So now you got to replace these old nuclear material rods with new, fresh uranium, and then you start the nuclear reactor back up again. And so in order to initiate a chain reaction for this uranium-235 nuclear fission, you've got to have a certain critical mass. And the critical mass for uranium-235 is 15 kilograms, or 33 pounds. The critical mass is the minimum amount of fissionable uranium-235 material that's required to generate a self-sustaining nuclear chain reaction. So you've got to have at least 15 kilograms of uranium-235 in order to initiate the chain reaction. So what we see here in this picture, there's your neutron that's going to hit or bombard the nucleus of the uranium-235, and it's going to cause it to split into your krypton-92, your barium-141, and then here are your 3 neutrons. Those are also products. And so this neutron is going to go on and hit another uranium-235 atom and cause it to split, but this time into some different products, strontium-90, xenon-143, and then again, 3 neutrons. And then again, those neutrons can go and hit other uranium-235 molecules, make new fission products, as well as make more neutrons. And it will continue to do this until there are no more uranium-235 molecules, atoms available to split. And this is what's called a chain reaction, a chain nuclear reaction. And so for section 7.1, there are 6 questions. The first 2 questions are related to isotopes. And so therefore, you want to have your periodic table handy so that you can answer questions 1 and 2. So for this isotope X, we need to find out the identity of this element. So its mass number is 119. And the atomic number is 50. And that's the number of protons. And so we need to just consult the periodic table to find the element who has atomic number 50. And that element is 10. Ten has the symbol SN. And so we will complete question 2 in class together. Question 3 is similar to the example that I worked earlier in calculating the delta M, the change in mass, and then using that change in mass to calculate energy. For question 4, if we have 1.8 times 10 to the 14th joules of energy that gets released in a nuclear reactor, what mass of matter in kilograms was used to create this energy? And so we're going to use the famous Einstein equation, but this time we're given energy, and what we're being asked to calculate is the delta M. So the delta M is going to be the energy divided by c squared. So the energy is 1.8 times 10 to the 14th joules. The speed of light, t 2.99 times 10 to the 8th, and we have to square it. And the units are meters per second, and we also need to square those units. And again, we want a change in mass. So that's therefore we need mass units in our answer. So we have joules per meters, joules second squared per meter squared. And so we need to use our conversion factor that we talked about earlier so that we can convert out the units. So now we have our meter squared, our second squared, and our joules canceling. And we're left with the unit that we want, a mass unit of kilograms. So I'll let you do that final calculation. Question 5 is completing the nuclear fission reactions and therefore filling in the blank for the missing product. So what is the missing product? For part A, we see that the sum of the superscripts on the left-hand side of the arrow is 240, 239 plus 1. And we also see that the sum of the subscripts, 94 and 0, which is 94. So therefore, on the right-hand side, the sum of the superscripts must be 240, and the sum of the subscripts must be 94. So let's look at what we have as far as superscripts on the right-hand side. We have 106, and we have 1, which is 107. But we need 240. So 240 minus 107. And the difference is 133. So this missing product must have a mass number or superscript of 133. Now let's look at the subscripts on the right. We have 45 and 0, which gives us 45. But what we need is 94. So 94 minus 45. That gives us 49. So our subscript for this missing product must be 49. And so now we consult our periodic table, and we're looking for an element whose atomic number is 49. And that element is indium, In. So that is our missing product on the right. So I'm going to leave B and C for us to do in our groups in class. Question 6 is comparing nuclear energy to energy produced via burning coal. So if anthracite coal has an energy content of 32 kilojoules per gram, how does it compare to the amount of energy released by the fission of 1 kilogram of uranium-235? And so fission of 1 kilogram of uranium-235, we go back to our example problem, that released 8.94 times 10 to the 13 joules of energy. And that was per kilogram. per 1 kilogram. So in order to compare two things, they have to have the same units. So coal's energy content is 32 kilojoules per gram. That's an apple, kilojoules per gram. But the uranium-235 energy released is in joules per kilogram. That's an orange. So you can't compare an apple and an orange. They either have to be both apples or both oranges. So we can take our 8.94 times 10 to the 13th joules per gram and convert it into kilojoules. Okay, that's in joules per kilogram. And we're going to convert it to kilojoules per gram. That way we've got the same units, and that way we can make a comparison. So there are 1,000 joules per every 1 kilojoule, and for every 1 kilogram, there are 1,000 grams. So now the joules are gone, the kilograms are gone. So now we can convert this into kilojoules per gram and then do a comparison of this fission energy with the burning of coal energy, which is 32 kilojoules per gram. And that gives us 8.94 times 10 to the 7th kilojoules per gram. Whereas burning coal only gives you 32 kilojoules per every gram of anthracite coal burnt. So you can see that you get a whole lot more energy in kilojoules per every gram of uranium-235 that's split than you do for every gram of coal that's burnt. So nuclear energy gives us, nuclear power plants gives us so much energy per gram of fuel than a coal burning power plant. So that is a very, very stark contrast. So let's talk about nuclear power plants. So the nuclear power plant, you have a nuclear reactor. And so it's a device in which your nuclear chain reactions are initiated by bombarding your uranium material with neutrons. These reactions are, as you can see, produce lots of energy. Very explosive if they're out of control. You don't want your nuclear power plant to blow up. So inside the nuclear reactor, these reactions have to be slowed down. They have to be controlled. And not only just initiated by bombarding with neutrons, controlled so you don't want your nuclear power plant to be a nuclear bomb. You don't want the reactions to happen so fast that they're out of control and you get an explosion. You want them to be controlled. And then you also want them to be sustained. You want that chain reaction to keep going at a steady rate. And so most nuclear reactors in the world, and definitely in the United States, uranium is your fuel source. So it's the uranium isotope that gets split by nuclear fission inside of the nuclear reactor. And the uranium fuel source is actually uranium-4 oxide, UO2. And so here are some pellets of uranium-4 oxide. You can see that they're about the size of a dime as far as diameter or height is concerned. And these pellets of uranium-4 oxide are placed end to end in these tubes here called fuel rods. And see, those are their UO2 pellets inside of the fuel rods. These fuel rods are an alloy of zirconium and other metals. And they're grouped into these stainless steel clad bundles that we call a fuel assembly. So there's your stainless steel, that gray, dark gray material that you see. The stainless steel is a protective covering over the zirconium alloy that contains your uranium-4 oxide pellets. And then these bundles are placed into your nuclear reactor, which is shown in this picture. So if you want to compare a nuclear power plant to your conventional coal power plant, you can see there are lots of similarities, but then there are also some differences. You see from this point, your nuclear power plant is totally identical to your coal power plant. That's pretty much identical. So those are your similar areas. What's different is that a coal power plant has a boiler and burner system. And in that burner, that's where the coal is burnt in the burner. And then the heat from the coal is used to heat water in a boiler to produce steam. And that steam then travels to the turbine. For your nuclear power plant, you also get steam that travels to a turbine and turns the wheels of a turbine, converting the kinetic energy of the steam and the heat energy of the steam into mechanical energy. The mechanical energy goes through a generator, and that mechanical energy is converted to electrical energy. And then that's sent to your home or your office building or your school, and that's your electricity. All that's the same. And then that hot steam goes through a condenser where it's converted from gas, water vapor, into a liquid condensate via a condenser. All that's the same. What's different is that the water coming out of the condenser of a nuclear power plant is hotter than the water coming out of the condenser from a coal burning power plant. And so the warm water first in a nuclear plant has to go through a cooling tower. And you may have, if you live anywhere near a nuclear power plant, the shapes of these cooling towers are very distinctive. You'll notice them. So they go through the cooling tower to cool that water off first before it's sent to your lake or your river. And then the other big difference, the coal-powered burning power plant burns coal in a burner, heats water in a boiler. And that produces the steam that produces the electricity. But of course, in a nuclear power plant, you don't have a burner and a boiler. You've got a nuclear reactor. So that's the difference between having a burner and a boiler, is you've got a nuclear reactor. Inside of that nuclear reactor, you've got your control rods, that rod assembly, and the zirconium and the other metals, such as boron, those help control the nuclear reaction going too fast and therefore exploding like a bomb. And then your fuel rods themselves contain your uranium pellets. Those are the red structures. Those are your fuel rods. That's where your uranium ore is contained. The control rods, they have the control metals. And some are metalloids. It's a mixture. It's an alloy, which is a mixture of different metals and metalloids. And those mixture of different metals and metalloids, which includes zirconium, boron, those help control the nuclear reaction so it doesn't happen too fast and therefore basically becomes an atomic bomb instead of just a nuclear reactor. And those control rods are very important in keeping the nuclear reaction slow enough so that you don't get an explosion. And not only do the control rods help prevent an explosion, but the cooling water is also very important, that you cycle cooling water in and out of the nuclear reactor vessel. That also helps control the rate of the nuclear reactions and prevent explosions. So the cooling water, you can see you have that primary coolant going in and out of the nuclear reactor, and it's connected to a steam generator. And inside the steam generator is your water, and that water gets heated and creates the steam that goes on to your turbine. So all that energy from the nuclear reaction goes into the steam generator to heat up the water to produce steam. And that is how you generate your electricity. It's from steam. So you're generating electricity from steam, whether you're using a coal burning power plant or nuclear, but it's how the steam gets produced that's different. So you can see the electricity generation is the same flow chart. Potential energy stored in the fuel molecules, whether the fuel molecule is coal or if it's uranium oxide. There's some type of ignition or reaction or burning of that fuel. For coal, it's basically the burner burns the coal, a combustion reaction. In a nuclear power plant, it's the fission, nuclear fission reaction that takes place by bombarding the uranium in the UO2 molecules with neutrons, causing the uranium atoms to split. And as a result of the nuclear fission, you get energy released, and that energy released is in the form of heat energy. That heat energy then heats water, converts it to steam, and then you have that kinetic energy of the steam sent to the turbine to be converted to mechanical energy. That mechanical energy is sent to a generator to produce electricity. So you can see the flow chart is similar for nuclear and fossil fuels. And the electrical energy that gets produced via your electrical generator. How fast is this energy, this electrical energy produced? Well, the rate or the fastness that electrical energy is produced is called power. And so power is a common the common unit for power is the joule per second. How much energy per unit of time? So power is equal to energy per unit of time. And so power is often expressed in joules per second, energy per time. 1 joule per second is equal to 1 watt. The watt is another popular unit for power. Single nuclear reactors have a maximum power capacity between 500 and 1,300 megawatts, as compared to just 600 megawatts for coal-fired power plants. Notice that a megawatt Mega means a million. So 1 megawatt is 1 times 10 to the 6 watts. And so you have a power plant in Arizona, Palo Verde. It has 3 nuclear reactors that collectively produce 1.2 billion joules of electrical energy per second. So that's the power, 1.2 gigawatts. And remember, the mega is a million. So a megawatts is 1 million watts. A gigawatt is a billion, 1 times 10 to the 9th watts. So therefore, 1.2 billion joules per second is 1.2 gigawatts. So if you want to know how much energy that these 3 reactors produce per day, just convert the joules per second into joules per day. And that will give you the amount of joules per day. And once you get your energy, then you can use the famous Einstein equation to calculate the mass in grams that's lost per day. And you calculate the delta M is going to be your E divided by C squared. And I'll let you finish that one in class. And then for question 2, based on our discussion of the nuclear reactor, match the following parts of a nuclear reactor with the letters A, B, C, D, and E. And so we said that only certain elements on the periodic table are radioactive. And so what does it mean for an element to have radioactivity? What is radioactivity? Well, the pioneer of studying the radioactivity of elements was Dr. Marie Curie. She applied the term radioactivity to mean that it's a spontaneous emission of radiation that only certain elements have the ability to do. And so she won 2 Nobel Prizes for her work on radioactive elements, one in chemistry and the other in physics. And so she discovered that there are many different types of radioactivity. And those various different types, we're going to focus just on 3 of those different types of radioactivity. And that's alpha radiation, beta radiation, and gamma rays. Now, let's say there are other types, but for the purpose of our class, we're going to focus just on the major 3. Alpha radiation, beta radiation, and gamma rays are shown here in this table. The symbol for each, their composition, what they're made of, their overall charge, and if an element undergoes alpha emission or beta emission or gamma ray emission, what changes take place to the nucleus of that element. So for alpha radiation emission, an alpha particle or alpha radiation is symboled the Greek letter alpha, which alpha radiation is synonymous or equivalent to the emission or the loss of a helium atom. So therefore, the change in the mass number will be 4, and the change in the atomic number will be 2. So when alpha emission happens, by an alpha particle being similar to a helium nucleus having 2 protons, and then also helium nucleus having 2 neutrons, giving a total mass number of 4, those 2 protons each have a positive charge, so the overall charge is +2. And so when an alpha particle is emitted from the nucleus of an element, there's going to be a change in the mass number of 4. The mass number will decrease by 4, and there's going to be a change in the atomic number of 2. The atomic number will decrease by 2. For beta emission, the beta particle is equivalent to an electron. And you can see it represented by the Greek letter beta, or being equivalent to an electron. So the symbol, lowercase e. An electron has virtually no mass, so the mass number is 0. And an electron is not a proton, so it doesn't have an atomic number. An electron is negatively charged, so you'll see it with a subscript of -1, meaning it has an overall -1 charge. And so a beta particle is equivalent to an electron. It doesn't change the mass number of the element when a beta particle is emitted from it, but the atomic number, therefore, will increase by 1 due to the loss of an electron. And then finally, your gamma emission. A gamma ray is symbolized using the Greek letter gamma, or you can also see it with the Greek letter gamma and a 0 subscript and a 0 superscript, meaning that gamma particles have no charge, and they also have no mass. So there's no change in either the mass number or the atomic number of an element when it emits a gamma ray. So we said that in order for nuclear fission to happen, that the nucleus of an element has to be hit by a neutron. So where do these neutrons come from that go on to hit the nuclei of elements and causes the splitting or the fission? Well, one way to generate neutrons is to use a radioactive element called plutonium, plutonium-238. You can also use beryllium-9 and also use alpha particles. And so plutonium is radioactive. So it will naturally split into uranium and then emit an alpha particle. This alpha particle can go on and react with beryllium and produce carbon-12, a gamma ray, and there's your neutron. And then this neutron then can go on and initiate nuclear fission. And so plutonium-238, I stated, was radioactive. All elements with an atomic number of 84 or higher are radioactive. That means they will naturally undergo nuclear fission. Those elements that are smaller with atomic numbers less than 84, they will not undergo nuclear fission. So radioactive isotopes are those with atomic number 84 or higher. They undergo decay until they reach a stable species, meaning one that is not radioactive. So uranium-238 with an atomic number of 92. It is radioactive. It will decay into thorium-234 with an alpha particle being emitted. And then thorium-234 with an atomic number that's greater than 84, its atomic number is 90, it will decay to Pa-234 plus a beta particle. So there's beta emission. And then Pa-234 with an atomic number of 91 means it's also radioactive, and it too will undergo natural radioactive decay. Excuse me. And so if Pa-234, it has atomic number 91, and Pa, its name is protactinum. It's one of those actinides that are at the very bottom of the periodic table. And so it will further decay into uranium-234. And so it may make more sense if I write it the other way. So if it decays to uranium-234, uranium is atomic number 92. Then the question is, what is the other product? So again, we remember that the sum of the superscripts must be the same on the left-hand and on the right-hand side. So on the left-hand side, you've got 234. Well, on the right-hand side, you've got 234, plus there's another product, so its superscript must be 0. The subscripts, you've got 91 on the left-hand side, but you've got 92 on the right. And so in order to make those equivalent, your subscript of this other product has to be -1. 92 plus -1 is 91. So therefore, this must be a beta particle, the other product. So this Pa-234 is undergoing beta emission, because a beta particle is one of our products. Remember, a beta particle is equivalent to an electron. So here is a nuclear decay series. Shown here in this graph for uranium-238. So you start off with uranium-238. The red arrows represent alpha decay, and the blue arrows represent beta decay. So the first thing that happens to the uranium-238, it undergoes alpha decay to produce thorium-234. Thorium-234 undergoes beta decay to produce Pa-234. And then Pa-234, as we showed here in our reaction, undergoes beta decay or beta emission to produce your uranium-234. And then the uranium-234 undergoes alpha decay, which is followed by 1, 2, 3, 4 additional alpha emissions or alpha decays. And therefore, those total 1, 2, 3, 4, 5 alpha decays converts uranium-234 into lead, Pb-214. And then after that, you get a series of 2 beta decays producing polonium-214. Along the way, you get bismuth-214, which can also undergo alpha decay to form thallium-210. And then once you keep going until you finally get to lead-206. And lead-206, Pb, lead is atomic number 82. And so this is stable. And that's when the decay series stops. Once you form a stable isotope, one whose atomic number is less than 84, and Pb's lead atomic number is 82, so less than 84, you get a stable element that's not radioactive. And therefore, there's no more radioactive decay because you've now got a product that's not radioactive. And so we have a series of 4 questions that we'll leave for our lecture. And so we should all be concerned about being exposed to nuclear radiation. And so there was a lot of debate over microwave radiation when microwaves first came out. Like, can microwaves cause cancer? Well, the answer to that is no, because microwave radiation is non-ionizing, meaning that microwave radiation has wavelengths that are too long, and therefore frequencies that are too small, and therefore energies that are too small to damage your DNA and cause mutations in your DNA. So if the waves are so small in energy that they can't remove electrons or mutate large molecules like DNA, then they do not cause mutations, and therefore they do not cause cancer. But there are some rays in our electromagnetic spectrum that are ionizing, like X-rays and gamma rays. X-rays and nuclear radiation, like gamma rays, alpha particles, and beta particles, they are ionizing. They can remove electrons from atoms and molecules, and therefore cause mutations, and therefore cause cancer. And so some sources of ionizing radiation in the US, radon, there are natural sources of it, nuclear medicine, such as undergoing nuclear magnetic radiation procedures, also X-rays are sources of ionizing radiation. So you should only get an X-ray, of course, unless it's deemed absolutely necessary that you need one. And so that's why X-rays are only given when it's suspected that there's something wrong and there needs to be an X-ray done, because you are exposing the patient to ionizing radiation. And that's why it's best to wear protective gear in an X-ray room to only expose a certain area of your body that needs to be exposed to the radiation. And so there's also ionizing radiation in things such as consumer products. There's a small amount. And then just natural sources, the soil, the air that we breathe, so on and so forth, has small amounts of ionizing radiation. And so where does ionizing radiation accumulate in the body? Your thyroid gland has the ability to absorb iodine-131, which is radioactive. Your lungs have the ability to absorb radon, uranium, plutonium, krypton. Your liver has the ability to absorb cobalt-60. Your muscles can absorb potassium-40, cesium-137. Bones can absorb many different radioactive elements. radium, strontium, phosphorus, and carbon-14. And so the annual dose is basically a measure of the damage that occurs to human tissue when a dose of ionizing radiation is absorbed. So there are three different main units for radiation amounts. The REM, which is called the Roentgen equivalent man, and it's going to be calculated by taking a factor called Q, which is a biological effectiveness factor, and multiplying it by another unit called the number of rads. A rad is a radiation absorbed dose, and it's the absorption of 0.01 joules of radiant energy per kilogram of body tissue. So you take the rad and multiply it by a biological factor, you get the REM. And then also you have the Sievert SV, which is 100 REMs. So those are the various units used to measure the amount of radiation dose that a person is absorbing in their body. And so, what is the safe amount of radiation to be absorbed by a tissue in your body? Well, you can either calculate the dosage in sieverts or REMs. If you're doing REMs, 0 to 25 REMs is safe. If you're calculating in sieverts, 0 to 0.25 sieverts is safe. There's no observable effect on the body. But once you go beyond 0.25 REMs, you start seeing some effects. 25 to 50 REMs, you start seeing your white blood cell count decrease because now your immune system is being compromised. 50 to 100 REMs, you get a drop in your white blood cell count and you start getting lesions. That means your tissues, your lymph nodes and things of that nature are being damaged and mutated. And then 100 to 200 REMs, you start feeling the physical effects, nausea, vomiting, hair loss. 200 to 500 REMs, hemorrhaging, ulcers, and possible death. And greater than 500 REMs of radiation is certain death. And so it's very important that if you work in a lab where there is high radioactivity present, if you're working with radioactive elements in that lab, or if you are a radiologist or a radiological technician and you're working with X-ray machines a lot, if you're working with NMR machines a lot, then you want to wear one of these little radiation counter things on your clothing every day while you're at work, because it's going to give you a count of how much radiation that you've been exposed to on a daily basis at the end of your shift. And then you'll know if you've overexposed yourself at any time during the day. And so that's why lots of medical professionals and scientists that work with radiation or in a radioactive lab on a daily basis, then they have to wear one of those counters that will count the amount of radiation that their body is absorbing, and to make sure that they're staying within this 0 to 25 REM range on a day-to-day basis. So how long do substances remain radioactive? How long, in other words, does it take a radioactive element to break down into a stable element, like we saw with the uranium-235 in our radioactive uranium-238? How long does it take uranium-238 to break down and decay down to this stable lead-206? Well, it depends on what's called the half-life. The half-life is the time required for the level of radioactivity to fall to 1/2 of its initial value. So all radioactive elements have a half-life. So in this graph, you have the percent of original plutonium-239 remaining on the y-axis, plotted versus time in years on the x-axis. So starting out with 100% of the plutonium-239, half of it will decay after 24,110 years. So plutonium-239 has a very long half-life, 24,110 years. And then for it to go from 50% to 25%, and therefore how much time for 25% of the original to decay? 48,220 years. And then when will you only have 12.5% of the original? After 72,330 years. When will you have only 6.25% of the original amount? It will take 96,440 years. So therefore, plutonium-239 has a very long half-life. So this little chart tells you how much of the original amount remains after a half-life and how much has decayed. So one half-life means that 50% of the original has decayed and you got 50% remaining. After two half-lives, you have 75% of it that has decayed and 25% remaining. After three half-lives, 87.5% remains. 87.5% has decayed and only 12.5% remains. So after every half-life, half of the original has disappeared. And you only have half remaining. So after one half-life, you got 50%. Two half-lives, only 25%. Three half-lives, 12.5%. Four half-lives, 6.25%. Five half-lives, 3.12%, so on and so forth. The next table shows you the half-life of certain radioactive isotopes, like the plutonium-239 we saw in the graph. Its half-life is 24,110 years. And then whether or not we use this particular radioactive isotope in for our nuclear reactors. And yes, plutonium-239 is used in nuclear reactors. So is uranium-238. Is present in the original fuel pellet. And then plutonium-239 is one of the breakdown products of uranium-238 decay. And then a lot of these others are fission products. They are a result of an original uranium-238 or uranium-235 or plutonium-239 decay. So you've got all these fission products. And then you see there are some on this list, like iodine-131, which is a fission product. It has a very short half-life, only 8 days. So if you're suspected of having a thyroid issue, then you're going to have to get your thyroid x-rayed. And one thing that you're going to be required to do is drink this iodine solution that will go straight to your thyroid, and therefore it'll glow in the x-ray because it's radioactive. But that iodine-131 that you drink, it'll be out of your body in 8 days. And then strontium-90 is absorbed by your bones, whereas iodine-131 is absorbed by your thyroid. And so therefore, bone x-rays, looking for bone cancer and so on and so forth, you may have to take a small amount of the strontium-90, but that's not good because it has such a long half-life. And if you're overexposed to strontium-90, it could result in death. And so you can see some of these fission products themselves and some of the original fuel, very long half-lives. And even some of their fission products have pretty long half-lives of about 30 years. But iodine-131 has a very short half-life. So does radon-222, just a matter of days. Plutonium-231, very short half-life, 8.5 minutes. And so we have 2 questions for section 7.5 that I'll let you answer in class. And that brings me to the end of the pre-class lecture.